Good afternoon, everyone. I'm glad to have the opportunity to present our work. The title of our work is Monitoring Smart App Homes from Encrypted Traffic. This is a joint work done by Wei Yan, Yugeng, Professor Zhu from Shanghai Jiaotong University, Xiaokuan and Professor Zhang from the Ohio State University. Here is the outline. Let's begin with the background. As we can see, smart home is a new concept of IoT, which enables the user to control multiple devices and let them work together. Nowadays, smart home is becoming more and more popular, and the market revenue is undergoing a rapid growth. However, smart home is still in its infancy. The reason is that the smart devices produced by different vendors cannot work together. So to solve this problem, smart home platform is proposed. The platform can enable different devices to work together and provide software application to control them. There are many popular smart home platforms, include Samsung SmartThings, Google Home, and Amazon Echo. In our paper, we focus on SmartThings because it's a popular platform and it's also a developer-friendly system. Now, before we talking about the system, it's necessary to have a brief look at the SmartThings. As we can see, SmartThings has three components. The first one is the cloud. Cloud is the brain of smart home, and it can remotely control the smart devices and host the device handler and the smart app. Device handler is a virtual representation of a smart device. For example, the smart light can be represented as a device handler with the capability switch and the commands on and off. Smart app is a Groovy-based program which can automate devices with their capability. Now, the second component is a local smart home. It contains the physical devices and the SmartThings hub. Hub is the gateway between the device and the cloud, and it connects all devices with wireless protocols. The protocols include Zigbee and Z-Wave. They have the features of low data rate, low power consumption, and encryption function. Now, the last component is the user interface. Now, with this architecture, SmartThings bring us convenience and benefit. However, it suffers from several attacks. The most important one is the misbehaving smart apps. It can conduct the two types of attacks. The first attack is the overprivileged accesses. In this attack, the smart app can control the device capabilities which are not granted by the user and perform some malicious actions. The second attack is event spoofing. In this attack, the smart app can spoof some event in the cloud backend and trigger the smart home to perform some bad actions. So to defend this attack, there are many existing work. These works include the flow control-based solution, context-based permission system, and the context-aware authorization. However, this method either requires a platform modification or need to patch the smart app. So the generality of this solution has limited. So is it possible to find a detection system without any changement on the existing smart home platforms? This is our goal, so we proposed our system HoMonit, a novel platform-independent anomaly detection system. In our system, without accessing the smart devices, smart hub, and cloud server, the only information we need is the wireless traffic. So the question is, can we detect smart app misbehaviors from its encrypted traffic? To answer this question, I will show a case study, and this study is the motivation of our paper. As shown in this picture, there is a smart app named Brighten My Path, which is used to turn on the switch when the motion is detected. We can see that when the motion is detected, a packet sequence will be transferred between the hub and the motion sensor. Similarly, when the switch is turned on, the wireless traffic will be generated to. We can find that the same device event have the similar wireless traffic pattern, and the different device event have different wireless traffic patterns. So it shows that the event traffic usually has unique and fixed pattern. The reason is that the protocols such as ZigBee and Z-Wave in smart home are designed for low data rate and low power consumption. Therefore, these protocols have low entropy property. It means that this traffic has unique and fixed pattern. I will introduce our another observation as shown in this picture. The working logic of SmartApp can be represented as the state machine. And we can also find the relationship between the traffic and the state machine. So for a current working SmartApp, if we can sniff their packet, we can infer the event and we can infer the working logic of this SmartApp. So if this working logic is inconsistent with that of benign SmartApp, it's highly possible that the SmartApp is misbehaving. So this is our basic idea of misbehavior detection. However, to translate the idea into reality, we need to address the following questions. The first challenge is how to extract the control logic of SmartApp. The second challenge is how to capture wireless traffic and conduct side-channel inference. The last challenge is about the implementation and evaluation. Now I will show the system design of our system. This is the system workflow of our system. As shown in this picture, our system contains two dominant modules, which are corresponding to the major challenges. Firstly, I will introduce the SmartApp analysis module. This module is designed to analyze and model the SmartApp. As we can see that in our paper, we utilize the deterministic finite automaton to model the SmartApp. The DFA is a 5-tuple, including the symbol, the state, and the transition. However, since the SmartThings support both open source and closed source SmartApp, so we need to propose two different methods to extract the DFA from them. Let's begin with the DFA building for open source SmartApp. We take a SmartApp SmartLight as an example. This SmartApp turns lights on when motion is detected. We can see its source code and we can use the static analysis to extract its DFA. Building DFA follows the two steps. The first step is using the AST builder to convert the source code into the abstract syntax tree. It's very easy. We can just use AST builder to achieve this goal. The second is translating the DAST to DFA based on our observation on SmartApp characteristics. I will show the details. Firstly, we need to infer the DFA symbols. We can see that the preference statements of the source code contain the capability information of SmartApp, and the subscriber method contains the command and attributes information of the capability. So by analyzing this information, we can build the DFA symbols. Now we need to determine the DFA transition to complete the DFA building. This is not so difficult. We also find that the subscriber method indicates the transition from the initial state to the intermediate state. And we also find the handler method is designed as the if-then-else logic. So we can determine the order of the transition from the handler method. So we can complete the DFA building for open source SmartApp. Now for the closed source SmartApp, the question is difficult. since we have no source code, we need to propose another method. Let's still consider the SmartApp Smart Light. Now look at the user interface of this SmartApp. We can find that to help the user to use it, this SmartApp provides some promote sentence, and this sentence contains the working logic of this SmartApp. So an intuitive solution is use the NLP techniques to extract the DFA. Firstly, we need to extract the text from the UI information. It can be done by using the UI automator. And then we need to infer the DFA symbols. DFA symbol inference is shown in this picture. We need to use NLP techniques to infer the symbols from the UI text and the capability candidates. However, directly applying NLP for UI text cannot achieve a good performance. The reason is that NLP performance highly depends on the training dataset. However, there is no adequate training dataset for the SmartThings platform. So in our work, our strategy is to reduce the candidate members before using NLP. As shown in this picture, for this user interface, we test all 200 devices, and the SmartThings will return 5 available devices. By analyzing these 5 available devices, we perform the intersection operation, we can reduce the candidate number to 1, and we will find the candidate is the switch. This is the picture. We can see that after we reducing the DFA, the capabilities candidates perform NLP will be more effective. Now we can use NLP method to infer the DFA symbols. We use the NLTK and word to back tools, and there is the infer the DFA symbols. Now the only thing we need to do is inferring the transitions. It's very simple because the UI design in SmartApps follows the symbol logical relationship. So the only thing we need to do is change the symbols according to the UI layout. As shown in this picture, we can obtain the transition and complete the DFA building. Now I will introduce another module. This is the misbehavior detection module. This module collects the wireless traffic and translates the traffic into smart device events, and then use the events and the DFA from benign SmartApp to infer the misbehaviors. Firstly, I will show how we infer the events. Firstly, we need to collect the traffic. In our paper, we collect 2 traffic. For the Zigbee traffic, we use a TI USB dongle to collect its packets. For the Z-Wave traffic, we use USRP to capture its packets. Then we need to remove some unrelated packets. As shown in this picture, we remove the beacon packets, retransmission packets, and other unrelated packets. After that, we need to fingerprint the events. In our paper, level-stand distance is used to measure the similarity between different packet sequences. As shown in this picture, for the event switch off, we active this for 50 times and perform and get its corresponding packet sequence. Then we calculate the level-stand distance between these sequences. And finally, we regard the sequence with the minimal level-stand distance as the fingerprint of this event. This table shows the events for all devices. This table shows the fingerprints for all device events in our evaluation. Now, since we can obtain the traffic and the events, the next thing we need to do is to inferring the event. So we bring a concept of burst to control the interval of traffic flow. Then we partition the traffic into several groups. We calculate the packet sequence between the group. We calculate the distance between the packet sequence and all event fingerprints, and we choose the event with minimal level stand distance as the inferred distance, the inferred event. Now, since we have the inferred events and the DFA from benign SmartApp, we can perform our misbehavior detection. We input our inferred events and try to transition the DFA from the start state to the end state. If the end state is the accepted state of DFA of benign DFA, it shows that this working SmartApp is benign. Otherwise, the SmartApp may be misbehavior. Now I will briefly show the evaluation result. In our evaluation, we chose 13 open source SmartApps from SmartThings, and 20 apps employ the Zigbee devices, and 10 apps employ the Z-Wave devices. And we evaluate the misbehavior detection performance for the overprivileged accesses and event spoofing respectively. Since we noticed that there is no available public misbehavior app dataset, so we need to build the misbehavior SmartApp according to the Fernandez way. Firstly, for the overprivileged access, we develop our overprivileged apps by adding some malicious code to cause unintended operations. And the detection strategy is to check the additional stats in the DFA matching. For the event spoofing apps, we follow the similar way, and the detection strategy is to check the missing stats in DFA matching. In our experiment, we use the true positive rate and the true positive rate to evaluate the performance. This picture shows the misbehavior detection result, and we can see that the average TPR for overprivileged access is about 0.98, and the TPR for event spoofing is 0.99. For some unsuccessful cases, the reason includes the packet loss, unexpected traffic, and signal delay. Now we will briefly discuss our paper. Firstly is about the generality of our paper. In our paper, we may focus on the SmartThings, but if the smart home platform has a similar architecture with SmartThings, our system can be deployed in these smartphones, in these smart homes. The second question is about the privacy leakage. Since we can use the side channel inference techniques to infer the current working event and the current working SmartApp, the user's privacy information, including their daily routines, home occupations, and health conditions, may be leaked. However, we point that this side channel inference attack is hard to deploy because it requires the attacker to place a sniffer very closely to the victim's house. Now I will briefly conclude our paper. In our paper, we propose an anomaly detection system, and this system leverages the side channel information techniques, and we propose some method about the DFA construction and the DFA matching. Our evaluation shows that our system can achieve effective performance. Due to the time limits, some information cannot be present. You can ask me questions and I will answer your question. Thank you.
We have time for a few questions. Hello, I'm Honda. I'm from Clemson University. I have a very quick question. So, I didn't see you have a false positive rate or negative rate present in your talk.
Yes.
Do you have that number? You have true rate there, but maybe I missed something.
We have this number on our paper.
Okay.
In the and we calculate and this table shows the true positive and true negative. For the false positive, we show that in our paper, and there is some false positive scenarios, because if the packet is lost, we may regard the smart app is a misbehavior smart app. We think it's a event spoofing.
Okay.
So it can be happen.
Yeah. Thank you.
And any questions?